Hi there, this is Brad Williamson, and this is a video to try to demonstrate how we might estimate parameters to fit a nonlinear expression like a Michalis-Menten enzyme kinetics equation like this. So it turns out that the Michalis-Menten curve looks like this. Your enzyme kinetics, where your reaction rate goes up. Substrate, there's a maximum velocity of your reaction. And then there's another parameter we're going to try to estimate, which is the substrate concentration where the velocity is 1/2 of the Vmax. So here we go. This is what we're going to try to get to, Km and Vmax. And we're going to try to get that from our experimental data. Now, these are 5 means that I got from an experiment using yeast as a catalase source and hydrogen peroxide concentrations in the floating filter paper disc method using that. So I converted those times of rise to reaction rates by taking an inverse, and here's my data. I don't have the error bars on there right now. We could do those, and they'd be very small down here and a little bit bigger up here, but there's no overlap between the 95% confidence intervals. But right now, we've got, there's the data, and that's what's plotted. Let's now actually let's estimate these parameters right here off of our graph as we have it right now. And so we could estimate our Vmax from this curve. It'd be really nice to have a data point here at 3%, but my experience, 3% in my filter paper discs coated with the yeast catalase, the reaction goes so fast that the discs don't sink to give me a chance to actually time the rise. So that's a very fast, so I can't get a data point here. I have to deal with just these. So I'm going to estimate that somewhere between 0.25 on my reaction rate and maybe 0.3. So I'll just put a 0.3 right here. I'll just put 0.25. Let's do that. Oops, sorry. 0.25 for my maximum. And then if that's the case, then somewhere right around in here in 12, somewhere between 0.5 and 1. So let's just put a 0.7 would be, you see 0.7 right down here. So I'll put 0.7 here. And those will be our estimated parameters for now. But so what? Well, we can actually plot them if we use this. Sorry, I didn't mean to move that over. So here we go. Let's just put this equation in right down here, our model. So this is actually a computational model of enzyme action. And we're going to see how well our data fits that model. So I put an equals sign to create this formula. And it's going to be Vmax. Let me put it in parentheses, however. Vmax right here. And I'm going to do an absolute reference on a Mac. It's Command T right there, puts those dollar signs in there, times my substrate concentration. And I'm going to want that to change, so I leave it relative. And I'm going to divide it by, I'm going to do another set of parentheses because I have a sum here in the denominator. And it's going to be Km, which is an absolute reference, Command T, plus this time, oops, excuse me, plus the substrate concentration. There we go. And if I hit a return, it should come out fairly close, 0.29, 0.03. That's pretty close, 0.029, 0.03. That's great. Oops, I slid sideways again. Let's copy those down, and you can see that now I have estimates based on the model and based on these parameters that are really pretty close to these. That's not bad. However, we can get closer. And what I've done here, excuse me, what I've done here is I've fixed up an area right here where I can put a plot, a line on here at the same time, and we can see where that line fits. So I'm in this particular column right here, I'm going to put the equation in again, equals let's do parentheses, equal Vmax. Again, this is absolute times the substrate concentration. In this case, the substrate concentration will be 0 for this part of the line, divided by Km, Command T, plus substrate concentration. Close this. Should come out 0. It does. Now, I've got this set of theoretical substrates. Every 0.02 all the way up to 4.0. And so if I copy this down to 4.0, there we go. And the reason that line suddenly just appeared is because if I click on that line, you can see that I've got that pre-selected already. And I have it formatted to only generate a line with no data points. So that's why that showed up. And this gives you an idea of just how the fit is. You see, it's not quite there. It obviously, our Vmax wasn't high enough. So let's make that a little higher. How about 0.3? Well, that's much better. Now, notice that it's now a little bit above that, but this is above it right here. So it could be if I pull this down a little bit by moving my Km this way. So let's do that, 0.8. Oh, yeah, I'm getting there. Yeah, that's pretty good. Now, how can we actually capture how much difference that is? Well, one is to subtract our actual experimental data from our theoretical data. In this case, this is our biggest difference right here. There's this experimental right here, and there's our theoretical right there. What's that difference? Well, we just simply do that, but let's square that difference. That's typically what we do here. So I'm going to do equal this one minus this one, and we're going to square that. So I'll put parentheses around it. That's, whoa, I must have made a mistake. I did indeed. Let's try that again. Equals this one minus this one. There, that's better. It's very small, but it's not 0. And now we move this down like this. And now I've created a measurement of how far each one of these points are from each other. And I've squared it. And so if I minimize this difference, I will get the best fit line that will fit in here. Now, how am I going to minimize that? Well, let's sum up all these differences. Equal sum. It's not very much. Now this is what we can actually minimize. If we look at it and get smaller and smaller, for instance, I could try 0.9, but that made it get bigger, so that's not going to work. So what could I do? Well, there's something called solver right up here. I've got it under here under the data tab. You may not have it there. It's different on a Mac, but this is, I mean on a PC, but this is what we're going to use here. Set objective. So actually that's what this number is right here. So I'm going to click here and I'm going to click right there as my objective. H5. Excellent. I want that to be small as possible, so I got it set for minimum. And how am I going to do that? Well, I'm going to do that by changing my parameter cells. And my parameter cells are these two cells right here. Okay, okay. Minimum, I tell it to solve this. Now watch, we've got 0.9 and 0.3 as our estimated parameters right now. Let's see what solver tells us. It's going to take just a little bit. I've got some other things flashing on my computer because there's a lot of work going on. It didn't take very long. 0.78 and 0.29. Wow, look at that. I'll tell it to keep that, and look at how that lines up. That's pretty accurate. Well, first of all, the data is unbelievable for me. To me, that's unbelievable considering the primitiveness of the technique we're using. But if you're really careful, it's pretty precise, and it really does a great job of fitting the theoretical experimental model, theoretical model of enzyme kinetics. So this is the model, this is our data, we fit it using these parameters, and if we look these parameters up on the activity of catalase, you'd see that they match up pretty good, but this is how we could actually compare, say, catalase from carrot versus catalase from potato versus catalase from yeast. This is what getting quantified is all about. Dealing with the curve and understanding how that curve changes as you move Km and Vmax. That's what quantitation is all about, or quantitative skills. It's kind of the end goal, but it's a tough one to get to, and not everybody's going to get to it. But this gives you an idea how you might want to do your curve fitting, um, and this video will hopefully make what I write about this a little easier to understand. So, okay, signing off for now.